Okay, moving on to the filled one. I think it's also called the solid sphere. And again, we're going to go back to what we were doing here. The two cases, one will be inside, and the other one will be outside. Now, when we have the empty one, like the shell, E was 0. But now we have the filled one. So what does a filled cylinder look like? It's all filled. And suppose its radius is also r. And I'm going to do the inside one first. Draw a Gaussian surface inside of, say, radius. Let's do B on the inside. So R will be B inside and R will be A outside. So when I do the inside, no matter how small or large I make the B, will it always have a charge enclosed? Yes? So that means I cannot make E equal 0 anymore. So that means for my inside case, my Gauss's law will be written as that. And this will be over the Gaussian surface. And this will be the charge enclosed. Do you guys want to guess what the answer is going to be? And remember, this is a spherical surface. So then this Q enclosed will actually be rho dV. And this would be E dA. What do you think the left-hand side will look like? And what would the right-hand side look like?
Why is it not big R on the right side?
Excellent question. Where are we? We are inside at point B. If we put the big R there, which is a very good question, it includes all of this charge. Is that charge enclosed in my Gaussian surface? So what will I get? Well, one of the B's is going to go away. And the 4 pi are going to go away. And I will get E in as rho B divided by 3 epsilon naught B hat. Now, if you do want to use R in your equation, you can. And how do you go about doing that? I'll show you. What is rho? Rho is charge per unit volume. If you want to use Q, you have to do 4/3 pi r cubed, where r was your total radius, right? So the total charge divided by the total radius. So if I plug that into the above equation, I can in fact write this as Q divided by 4 pi epsilon naught, but in this case, it'll be B divided by r cubed, but still B hat. Does everybody understand how we got that, right? Yeah, it's just literally plugging this in here. Okay, now what about outside? Come on, let's choose a Gaussian surface. And I'm going to use this Gaussian surface, and this is going to be my radius A. Step one, write Gauss's law. So step one, E dot dA equal Q enclosed divided by epsilon naught. This side is my Gaussian surface. This side is my charge enclosed. So this side becomes E 4 pi A squared. And this side becomes rho over epsilon naught, and dV will be 4/3 pi r cubed. Do we all understand it should be integrations and stuff, right? I'm just writing the answers. They're all integrations. You should do all of them every time. Or E outside can be simplified to rho over 3 epsilon naught r cubed over A squared A hat in order to make it into a vector. Again, rho is nothing other than charge per volume. Plug this value in here. What do I get? E outside Q over 4/3 pi r cubed 1 over 3 epsilon naught r cubed over A squared A hat. Threes will go away, and r cubed will go away. And what am I left with? Drum roll. 1 over 4 pi epsilon naught Q over A squared A hat, which is identical to the E field created by a point charge.
So for the outside of an empty sphere, we use sigma A or sigma dA. And then for a filled sphere, we use rho.
Yeah, well, okay, so be very careful. So what is an empty shell? We are talking about the charge enclosed, correct? Where does the charge reside in an empty shell? Only on the shell itself, right?
Yeah.
So even if you were to take the dV, what's inside the dV?
Nothing.
Nothing. So you can't use it. But if you have a filled one where there's charge everywhere, then you have to use the volume integral. And I want to show you something even more fun. Okay. So if you were to draw what it looks like So this is your empty shell, and I want to draw it. What's the E field at different points? So suppose this is your R. What's the E field inside the empty shell? 0, right? And what's it outside? It varies as almost 1 over R squared. And it looks like this. So what happened between these 2 points, point A and B? That confused me for a long time until I realized that there is no magic that's happening. No matter how thin you make the walls of your charged shell, there's always a small thickness. So in fact, you should be looking at it like this. And the magic that happens between these 2 points is this. So it goes ding, 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 ding. Then it kind of goes like that. And then it goes like this. There is a increase when you go from the inside to the outside of the field on a shell. Except we don't think about that. On the other hand, for a filled shell, when we were doing this case here, what's the field look like? Is it 0 on the inside? Nope. What it is actually is pretty constant. It's proportional to R, right? It's proportional to this number. So be very careful. Look at this. E in is proportional to B. As you increase B, your field goes up until it reaches the surface, and then it goes as 1 over R squared. Here. Good?